Okay, this is now lecture 2 in oceanography. This is also chapter 1 in your textbook that you should be getting by now if you've not already gotten it. And this topic is an interesting chapter because it's sort of a grab bag of all the basic foundational topics that you sort of need to understand to go into oceanography. So there's a little bit of everything: origin of the Earth, origin of the solar system, origin of the planets, origin of the moon, origin of the oceans, of course, which is most relevant to us, the atmosphere, origin of life. I mean, everything but the kitchen sink is in this chapter, although done in a very quick and dirty fashion because they didn't want to make it too long. On top of that, they talk about the scientific method and some other things as well. So this is going to be a fairly large lecture. I will probably do it in multiple parts, so you can watch it in multiple parts as well. And certainly we're going to take up most of our time in the first module. When I give it in a regular course, it's usually about 3 or 4 lectures to get through the whole thing. It's about, say, 6 or 7 hours of material. And I will cover it at a little higher level than you might in a introductory oceanography class, a 100 level class, because we are a 300 level class, or now 3000 level class, and we're supposed to have a little more rigor. So yes, I'm using a book that's mostly for the introductory level, but I'm adding things in like this chapter. I'll add a lot more detail and a lot more rigor so that you are really doing a 3000 level course, not just the superficial version that's in your chapter. And hopefully you'll understand things better because I'm not just going to skip over and make a lot of declarations that this is how things work and then without explaining why. Okay, so let's launch into it here. Let me switch over to my PowerPoint and set up here. So the chapter has some name, but this is really a origins of everything chapter. It covers everything, as I said, the origins of the Earth, the solar system, the moon, the planets, the oceans, life, just about a full spectrum of different things. Plus, it has a section on the scientific method at the beginning and some other odds and ends too. And so let's start with some sort of general introductory thoughts just to sort of capture what oceanography is about. Now, you have to think, we go back to the early days of human knowledge about the world, oceanography's earliest days, in other words, that the world, as most people knew it, was mostly land. The people who were, even those who were on the edge of the Mediterranean, most of them were not great sailors and didn't spend a lot of time in the ocean because it was a dangerous place, in many cases, a very deadly place. So most cultures are still land-based, and they did very little exploration outside the area of what was in the known world. So for them, for example, the Mediterranean was the largest body of water they knew of. And of course, the Roman Empire, as you might recall, completely encircled the Mediterranean, where it's got its name. Mediterranean means in the middle of the land. Midi is middle and terra is land. It's the middle of land as far as they're concerned. This is the world that's mostly covered by earth and land, and water was not that important to them. The Romans actually called it Mare Nostrum, which literally means our ocean or our sea, because they owned the shoreline all the way around it. They knew about the Black Sea, of course. They may have known about a little bit about the Caspian and other lakes that are now gone. But they rarely sailed far from the side of shoreline because it was too dangerous then. Navigation was too unknown. Very rarely ever ventured out into the Atlantic. It was pretty much an unknown place that they didn't explore at that time. So there was very much a limited knowledge of the world. I mean, the people and the cultures of Mesopotamia and Egypt very seldom went very far outside the world. And even the Romans who conquered virtually all this unknown world in their heyday really didn't understand what they were dealing with. And so that's the way the world was thought of for that time. The world was virtually all land. And now, ironically, as we can now see the entire world in a way that they could not, especially when we look at it from space, what's very obvious is that, in fact, the opposite is true. The world is mostly oceans, about 70% ocean and 30% land. Famously, the NASA astronaut by the name of Lawrence Shriver said, when you're circling the Earth every 90 minutes, what becomes clear is that it's mostly water. The continents look like they're floating objects, okay? So that's the first takeaway here, is that, we are the ocean planet, and we're, as far as we know, the only planet anywhere that has liquid water in large quantities in oceans of that size. Okay, certainly nothing else in the solar system has liquid water oceans, let alone ones that take most of the planet's surface. And even more startling, we'll focus on this later when we talk about this and talk about the beginnings of oceanography, nobody knew what was under all that blue. Okay, the ocean completely covered 70% of the Earth's surface. And it was not possible in most cases to know very much about it, as we'll talk about when we get to that lecture in a couple of weeks. And I remember growing up, the maps and the globes that I have all had pale blue, which was pretty much unbroken except for islands that popped out of it. There was no information about the sea bottom. And so when we look at a map like this that now has the sea bottom shown, that is a relatively recent discovery since the late 1950s. In fact, the woman who figured it out was a woman named Marie Tharp, who I'll talk about later in this course, and her partner Bruce Hazen were the two more or less mapped the entire world's surface. And so Marie Tharp is thought of one of the great scientists of all time, let alone one of the greatest women scientists of all time, because she mapped more of the Earth than any person ever has or ever will. Okay. So we didn't know what 70% of the Earth's surface looked like until just now. All right, now let's break the oceans down a little further and talk about their distribution. Okay. You can describe the oceans in terms of just 5 oceans because they interconnect, especially when they connect through the Southern Ocean, which connects all the major oceans around the world. Just the Pacific, the Atlantic, the Indian, and the Southern Ocean is 4, plus the Arctic is 5. Okay. And in terms of size, 50% of the Earth's the oceans are in the Pacific all by itself. And I'll show you in a moment all the world's continents fit in the Pacific if you wanted to try to do so. The Atlantic is only about half as wide as the Pacific. Okay. The Indian Ocean is just slightly smaller than the Atlantic. And again, where you define the ends of these things is sort of arbitrary because they all merge with the Southern Ocean at the bottom. And then the Arctic Ocean is only about 7% the size of the Pacific, and it's also extremely shallow. And then, as we said, it's commonly the case nowadays to refer to the giant body of water that circles the Antarctic as the Southern Ocean because it's distinctive in the way it behaves and its temperature and its salinity. There's a sharp boundary here where the world's ocean currents circulate around the Antarctic, separating it from the other world's oceans. So it's really not part of any of the other oceans. All right, so there we think about it as 5 oceans. With the Southern Ocean, or here we have 4 oceans if you take away the Southern Ocean, and 3 oceans, of course, if you take away the distinction between the Arctic and the rest. So 5, 4, or 3 oceans. Here's 3 oceans here, just Atlantic, Pacific, and Indian, okay? But they're all basically one ocean. Another graphic to show this different ways. So for example, here is the amount of land area in yellow, roughly 30%. Here's the amount of ocean in blue, roughly 71%. Okay, and of that 71% of your surface here, we can subdivide it further. Almost exactly half of it's Pacific. Another exact quarter of it almost is the Atlantic. And then 20% or a fifth of it is the Indian Ocean, and there's the Arctic Ocean. This one, of course, is not keeping the Southern Ocean in the calculation. Now, that isn't the way it's always been, right? We talk about 5 oceans or 4 oceans or 3 oceans, depending on which way you want to divide them. But in reality, in the geologic past, there have been different configurations, especially around 250 million years ago in what we call the Permian period. The Permian period was a period when all the continents assembled into one supercontinent called Pangaea, which stretched all the way from just roughly over the North Pole all the way to the South Pole. Of course, Antarctica was not on the South Pole, then it was Australia. One supercontinent, Pangaea. We're going to get to Pangaea a lot in the next couple of weeks. And so that meant 70% of the Earth's surface was again an ocean, but it was one ocean that wrapped completely around the other side of the Earth. So in this view, almost no land is visible at all. Okay, and this is the incorrect label. This is now called the Pan-Thalassa Ocean, and that just really means in Greek all oceans. Pan is goes all, and Thalassa is the old Greek word for oceans. So it was one ocean which covered 70% of the Earth all by itself. Very different kind of planet than we have now. All right, now let's break it down. The largest, of course, as we just said, is the Pacific. 50% of all the ocean's waters and all the ocean's surface is Pacific. So big that continents fit inside it, right? If you've ever flown across the Pacific, say to Asia or to Australia, it's a whole day's flight, 12-hour flight typically. And of course, throws you a whole day off because you cross the international date line right about here and do a time warp and go forward in time by a day. And then, of course, flying back, you get that day back. Right, so there are ways in which you can rotate the globe where you can pretty much see nothing but the Pacific Ocean, with just a little bit of land on the fringe here in this perspective, right? All by itself, it's almost half the Earth's surface. Okay, that's really startling. If I teach this in a classroom and I have a globe that's on a rolling stand where I can turn it in any direction, I usually do that. I will roll the globe over so you can see just the Pacific from the perspective of sitting on your seat and facing the globe in the front. And almost no land is visible except the very, very edge of this thing. And to prove it for you, here we go. Here's a projection of Pacific Ocean. Here are all the continents to scale, okay? And there they are, patched in. As you can see, they all fit pretty much inside the Pacific Ocean. And now the Atlantic, of course, our second big ocean, about half the size of the Pacific, or about a quarter of the total amount of ocean surface. And that has been smaller in the past. The Atlantic didn't exist 70 million years, or 170 million years ago. And then the Indian Ocean, slightly smaller still. Of course, it merges with the Southern Ocean down here. So it's really sort of arbitrary where you call the Indian Ocean its boundaries. And then the smallest and shallowest of all this is the Arctic Ocean, bounded by all the northern edges of the continents. It's only about 7% the size of the Pacific, so it's a very small percent of the whole Earth's surface. And then, as I said, this ocean right here that surrounds the Antarctic, which has its own set of spiraling currents that go around it and separate it from all the rest of the ocean's currents and all the rest of the ocean's influences, is often called the Southern Ocean, because it really does behave in one ocean, and it's different behavior from the Atlantic, Pacific, or the Indian Ocean. Okay, and some people always ask me in this class, so let me answer it right now. If you're familiar with ancient literature, especially reading Sinbad the Sailor and 1001 Arabian Nights, the famous story told by Scheherazade supposedly to Sultan to keep herself from being beheaded. The story of the 1001 Arabian Nights frequently mentions the seven seas as they were known to the ancients. And remember, the ancients did not venture out to the Atlantic or very far from the land at all. And so the original seven seas that the people in the ancient world of the Mediterranean, North Africa, parts of Western Asia, they knew of the Red Sea, okay, which is right down here. The Mediterranean, of course, the biggest one they knew. The Persian Gulf was a body of water they recognized. The Black Sea, of course, they recognized. The Adriatic Sea, enough Asians had to experience the Adriatic Sea, so they knew about it. And the Caspian Sea, which is not shown very well here, but it's right there. And then the Indian Ocean, okay. They didn't often separate the Adriatic, although it's shown there distinctly. Okay, and so that's interesting because here we go. There's no separation of all these continents, of these oceans, the way we think of them now. And they didn't even know about, say, the North Sea out here. So there's the original seven seas that the ancients knew. This is only the world the Romans knew, the Greeks knew, the Phoenicians were the first great sailors on the Mediterranean, and they knew the Mediterranean pretty well. But again, they rarely traveled very far from the side of shore because they couldn't navigate very far. The Romans actually were quite poor sailors, even though they ruled the entire world. They really hated fighting on the ocean, and they did all they can to fight on land only. And then they had fleets when they needed them, but they were not a seafaring nation like the Phoenicians or many of the Greek city-states were. This is another staggering thing to think about when you think about the oceans, okay? You look at the giant size of the globe and you see all that blue on it and the projections I just showed you a moment. And then if you talk about volume, however, here's the volume of the entire Earth. And here by comparison is the entire volume of the ocean waters on the planet. And that's how they compare, okay? So if you actually spread this little droplet out across the entire surface of this, it's a thin little film of water kind of compared to the size of the Earth. And this tiny droplet here is all the fresh water on Earth, including the glaciers and the ice caps, which is even a smaller total volume. So again, the oceans look impressive because they cover the entire Earth's surface up to 70%, but when you actually compare volumes, they're tiny in comparison. Now, of that percentage of water that's on the Earth's surface, as we said, the majority of it's in the oceans. In fact, 97% of it's in the oceans. So, you know, to a first approximation, almost all the world's water is in the oceans. We're going to talk about how that changes as the water moves around from the oceans to land, to rivers, to glaciers, and so on. All the remaining, barely 3%, is in the other parts of the world, not in the oceans, such as almost all of it in glaciers and ice caps, another 0.5% in groundwater. And look at the tiny amount that's in freshwater lakes, 0.009%, 0.008% in inland seas, soil moisture, 0.005%, stream channels, 1/100%, and the atmosphere, 1/1000%. Okay, so tremendous amount of water, and yet almost all of it's in the ocean. If it weren't for the evaporation of water off the ocean to the land, none of this would ever exist either. It would all stay in the ocean. Oops, too fast. All right, now let's talk about some scale issues. We talked about oceans in terms of how they cover the Earth's surface, where they look very impressive. But we also mentioned how they're very, very shallow compared to the size of the Earth. Nonetheless, there's shallow and there's deep, and then there's really deep. Okay, and so just a little bit of sense of perspective how different bodies of water compare in terms of depth and height. Okay, so for scale here, for example, this is the highest building, which is the one up in Qatar. That's or it's in Trushloman, I think, which is this huge, tall skyscraper they built, slightly smaller than the one that's in Singapore. Okay, and then here are some other things for scale. Here you can see some super tankers on the ocean, a few other things. Here are some of the more familiar bodies of water on land, and here are the highest mountains and plateaus on land for scale. All right, and then here we go. We have shallow oceans, like here off the coasts of many parts of the world, what we call the shallow continental shelf, which we'll talk about in a later lecture. And then it gets slowly drops into deeper and deeper water. When we get to the deepest part of the ocean right here, 4,000 to 5,000 meters or 4 to 5 kilometers down, we're talking 20,000, 30,000 feet below sea level to the deepest part of most of the oceans. And then in the middle, as we'll talk about later, there are things like these seamounts and mid-ocean ridges which stick up through that. But this big flat area of the oceans, which we're going to get to in a few more weeks, called the abyssal plains. And that makes up most of the deeper part of the ocean. However, there are deep things, and there are really deep things. So at the edges of certain continents and islands, we have these oceanic trenches, which we'll talk about later, are caused by subduction. All right. The deepest of which is the Marianas Trench, okay, which is 33,000, 11,000 meters deep or 35,000 feet deep. That's deeper than Mount Everest. So if you took Mount Everest and stuck it in here, you'd still have another 10,000 feet to go. Okay, that's how deep the Marianas Trench is. It's the highest or deepest feature on their surface, much deeper and below the sea level than the Mount Everest is above sea level. And for comparison here is a profile of the Marianas Trench without this vertical exaggeration. It's actually a very gradual feature, even though it's enormously deep. And here is one of the big island of Hawaii. This is Mauna Kea, one of the cones of the volcanoes on the Big Island. For comparison scale, you could almost take the Big Island of Hawaii, flip it upside down, it would more or less fill the Marianas Trench. Okay, so a very striking thing. The world's deepest spots are in these trenches, like the Puerto Rico Trench, but the deepest in the world is the Marianas Trench. And that's this little animation here. Let me switch over to my browser. Hang on. So let me switch. Open my browser first and share to my browser. Chrome, share. And now, open this ride. You should all see my browser here, and we're going to have a little animation about the Marianas Trench. Gives you a sense of scale and perspective here. It's an enormous valley, deeper than the Grand Canyon by 10 times deeper, actually. It's all the way to the deepest part of the surface. So this is a digital map of it. Imagine, of course, it would be very dark there, no light at that depth. Pressure is enormous. 33,000 feet, 5,000 feet, deepest spot. Okay, and let me put my headphones back on here, and let me share back to where we were, the PowerPoint. Okay, and return to our slides. So there we go. There's a link if you want to play that short little clip again. All right, so that was sort of a taste of what we're talking about here, a taste of how oceans are thought of, a taste of how they're thought of historically, a taste of their scale and how big they are, just sort of a perspective on what oceans are like. Now, the next thing your chapter has in after that introductory material I just finished is a short discussion about the nature of science. And this is something I often like to talk about in just about every class I teach, especially classes which are full of non-majors like this one usually is, because most of you have a very distorted notion of what science really is, at least as scientists practice it, okay? It's very much the case we get these people who sort of think science is some kind of a cut and dried thing when you're always wearing a white lab coat and all the rest. And it's not helped by the fact that if you had a science class in high school or middle school, there's often a very short chapter near the beginning of your textbook, which gives you this very cardboard, cut and dried, and basically false image of what science is really like. Some good high school textbooks do better than those. I've seen the ones my son uses, but most of them are pretty far from what we actually do. And the first problem we have here, of course, is a cultural stereotype problem. The science is this mysterious, witchcraft practiced by people with brains and thick glasses and all the rest. And the particular stereotype, of course, is always white lab coat, a wild hair, usually a male mad scientist of elderly age, but there are now stereotypes of female mad scientists as well out there in the media. And this is, of course, all about Hollywood, right? This has nothing to do with reality, okay? Right? This is about wearing a lab coat. Well, I am a practicing scientist and have been for over 40 years. And the last time I wore a white lab coat was when I had chemistry lab in freshman year in college, which is almost 45 years ago, okay? So lab coats don't define you as a scientist, okay? Although people use them as props and wear them, for example, in videos to make them look like a scientist or what people think they should be like. The only people who actually wear lab coats in science are people who work in medicine or in chemistry, places where you're likely to get splashed by chemicals or other nasty things that you don't want on your street clothes. That's the only reason to wear one. I don't work that kind of science. I used chemistry lab since sophomore year in college, okay? So I don't wear a lab coat and I haven't worn one in years, okay? So that's not what we define science by. It's not by wearing a white lab coat. It's not by having bubbling beakers and sparking Van de Graaff generators. Those are all stereotypes, okay? Science is not about the clothes you wear, your lab coats or whatever toys you play with. It's a method of looking at the world, okay? In fact, what's distinctive about it, it's the only method we have left on the planet, basically, that's continuously criticized, cross-checked, fact-checked all the time by a method that's called peer review, which most of the public doesn't understand very well. They say, oh, well, science is like anything else. No, it isn't. Science is self-correcting because anytime you try to publish a scientific paper in any reputable journal, as soon as you submit it, the editors will send it out to 2 or 3 or 4 sometimes or more reviewers whose job it is to really tear that paper to pieces and to find the flaws in it. And they are completely anonymous most of the time, so they can say any nasty thing about you they want, and you can't answer them because you don't really know who they are. And if they tear your paper to pieces, usually the journal will reject your paper, or they may send it back to you and say, well, fix this, and then we'll review it again. Okay, so to get a paper published in any reputable journal is a long, slow process, often months to years. And it's all because it's very carefully checked by the people they send to review it. There's nothing else on the planet anymore that has that kind of degree of scrutiny and fact-checking and quality control, okay? I mean, the media really have big problems, as all of us know, but so does the internet, right? People get all this garbage off the internet. The cesspool of lies is what I call it. 95% of stuff on the internet is false, and yet people trust it for all sorts of wrong reasons, okay? Especially, as you know, if you do your average Google search, Google remembers what you search, and then they will always try to find matches of similar sites. So they will tend to send you down a rabbit hole of all these similar sites and get you more and more confused and lied to all the time, okay? So science is constantly being tested against the outside reality, okay? And it's self-correcting. And science has limitations. Well, we don't pretend to know anything about the supernatural. We don't pretend to say why the world was created, right? That's an ultimate cause, as Aristotle has said. Those are questions that are not in the realm of science, okay? In particular, science is about naturalism. We can only deal with the natural world, with things we can test, observe, and determine if they're real or not. Anything supernatural, where it's a miracle or a religious statement, the statement Zeus did it, right? You can say, well, it's true, I believe it. It may or may not be true, but it's not a scientific statement. We can't evaluate that, okay? And it doesn't that science doesn't want to deal with supernatural. It's that it's not a useful way to get forward in terms of understanding the world. If you say Zeus did it, then that ends the inquiry. Nothing more is allowed to be explained, okay? What they call them science stoppers. As soon as you resort to a supernatural cause, you end all the scientific discussion. This famous little Sidney Harris cartoon says it very nicely. We have all these calculations on the board here, and then a miracle occurs, and then the rest of the calculations, and the caption says, I think you should be more explicit here in step 2, right? In other words, miracles are not something scientists deal with or can deal with. So what is science? It's not white lab coats or bubbling glassware or any piece of equipment. Again, as I said before, it's a method of thinking about the world around us, and only the natural world. We can't answer supernatural questions. And the central idea of most of science is about testing hypotheses, right? That part your high school textbook probably had right. We set out an idea, an explanation about what was going on in some part of the natural world. That's a hypothesis, and then we try to test it. But we find, if you look at your science textbook, they'll say, oh, well, we find facts that confirm it, prove it true. And we're in real science, right, in the science of actual scientists and the philosophers of science, that's actually not how it works, right? For example, if you find lots of observations which seem to confirm your observation and your explanation, you say, for example, my hypothesis is all swans are white. And that's what's called an inductive generalization in the language of philosophy of science, right? That everything fits this observation. Well, no number of white swans will ever prove that statement right. You could just find 1 million white swans, and you still would not have proven it right. But one non-white swan falsifies the statement, proves it wrong. This is the famous black swan of Australia. So science is not about proving things true. It's about trying to prove them wrong, rejecting them, and then getting a better explanation. The famous British philosopher Karl Popper was the pioneer in this kind of thinking about a century ago. And he said, science is about being testable, falsifiable, is the way he would describe it. His title of one of his books, Conjectures and Refutations. You try to refute ideas that have been proposed by other scientists and prove them wrong. If you haven't done so, well, then the scientific idea might be more rigorous. It might be better supported. It's what we call corroboration, when you have shown that your observations have not falsified something. But at no point do you ever prove something right, because you can't. Theoretically, philosophically, you can't. You can only prove things wrong. Okay? So here's our observation, let's say. Collect a bunch of facts about the world, and then we set up a hypothesis, a tentative, testable statement. Then we go around and test it. We look for observations or models or experiments or anything we have to shoot it down and redo it and hopefully revise it. And then when you've reached the point where you've done that, where you've hit it over and over again with lots and lots of independent observations and tests, and it survived every one of them, then corroborated, as we say, every time, then it reaches a very high status in science. It reaches the idea we call a theory, which is a very well substantiated explanation of some aspect of the natural world that incorporate facts, laws, and logical inferences and test hypotheses. Right? Theory is the highest quality of highest level of scientific certainty we have. Okay, you probably know this if you watch your younger siblings. Right? They'll make an observation, interesting object on the floor. They'll try to find a form of hypothesis about it. They'll perform an experiment. They'll lick it. They'll analyze the data and report their findings. When they discover it tastes bad, and then you invite the others to reproduce the results. Okay. Now, as I mentioned, we were to use here the word. You mentioned the word theory here. It's very probably a big problem in our culture where the word theory actually has two completely different meanings. In science, it's one of the best established ideas in the entire realm of science. But to the public, the word theory means a wild guess, a wild speculation. And so people who want to discredit science, like creationists, for example, they'll often say, oh, well, it's just a theory. And they're using the wrong sense of the word theory there, okay? Because in fact, that's not what it means to a scientist. So theory, as I said before, in the public is a wild guess, like all the various theories of who assassinated JFK is an area where you have lots of wild guesses, okay? But that's a totally different meaning the word that scientist has, right? To a scientist, a theory is a well-established explanation of the natural world, explains all the known observations, right? So sure enough, evolution is a theory in the good sense of the word, the scientific sense of the word, but gravity is just a theory. And yet you're not floating out of your chair as you listen to this, I presume, okay? There is a germ theory of disease, right? We didn't know until the beginning of the 20th century that viruses and bacteria cause most diseases. And nobody knew that before then. Instead, they used leeches to bleed people to death. Okay, the germ theory of disease has pretty much invented modern medicine and saved millions of lives, even though right now we're finding a virus that's very hard to stop. So the germ theory of disease is just a theory, but again, without it, you'd all be dead. Okay, and yet, as we said, the public, especially creationists and religious fundamentalists, have always misunderstood the word, just as a way of basically getting around evolution. This was Reagan when he was running for president in 1980, talking to his religious audience. And he says, well, it's a theory. It's a scientific theory only. And in recent years, has been challenged the world of science. That is, not believed in the world of science to be as infallible as it once was. Let's unpack that amazing statement. I mean, it incorporates more misunderstandings of science I've ever seen in a single sentence than anywhere else, okay? First of all, number one mistake is mistaking use of the word theory. And the sense the public uses it, which he is not the way the scientist uses it, right? The theory of evolution is actually the best substantiated idea in all of biology, okay? And so that's not a good, not a bad thing, okay? And it's in recent years been challenged the worlds of science. Okay, if you learned what we just talked about, everything in science is constantly challenged, tested, falsified if possible. If you stop testing it, you're stopped doing science. So it's supposed to be challenged, okay? That's not a bad thing, okay? In religious systems, right, you don't challenge anything. But in science, you're always supposed to be challenging things. And then he says, that is not believed in the scientific community as infallible as it once was. The word believe, infallible, those are religious words. No scientist believes in evolution. Scientists accept evolution based on evidence, right? The word belief doesn't belong in science at all. And nothing in science is infallible. That's the whole point of falsification, right? That we are always trying to test ourselves and prove ourselves wrong. It's a good thing that things can be proven wrong because that leads us to a better hypothesis, hopefully someday to the truth. So this is about as back-asswards as you could ever say describing science. Okay, and so we run into battles with pseudoscience as well as with religion and Marxist politics and many other areas, which are belief systems that do not allow challenge, do not allow testing. They're not scientific in any way. And so these are some of the things we've now talked about, right? We never prove an idea true in science. It's impossible. Nothing can be ever proven true. It's either falsified if we shoot it down or corroborated if it's supported, okay? And we're not about final truth. Scientists are always aware that they're always being on the slightly better path to things, but they're getting a tentative provisional explanation of the world. The best explanation at the time. We always know that it could be wrong in the future, although many ideas we doubt will ever be proven wrong, okay? And so this is the big difference. Now, scientists, when they're talking to the public, don't talk in these terms, right? They don't use testability and falsifiability the same way. They often have to talk about ideas like evolution in more dogmatic fashion because that's the only way the public will understand it, okay? But that is still what they think in the back of their heads, right? Every idea in science must be tentative and provisional, right? That can be tested and falsified at any time or it stops being science, okay? We should be welcoming to be proven wrong. And we should always be looking to shoot down our own ideas and find better ones and never expect to reach a final answer. Now, that's hard for humans, especially scientists. We're humans with egos like anybody else, and we hate it when somebody else proves us wrong. But ultimately, that's better for our science if it happens and we are indeed proven wrong, okay? We don't speak about facts or final truth in science, at least not to each other, okay? We spoke about well-corroborated hypotheses. We're talking about probabilities that X is true. And what science deniers like creationists and climate deniers often do is say, well, they're not 100% sure that X is true. Well, of course, nothing in science is 100% anything, right? That's a mathematical statement. Mathematics is 100%, not real world science, okay? I could say it's 99.99% sure that if you jump off a 15-story building, you'll die, but there is a 1 in 1,000th chance you might survive it, right? But I don't think most of you want to take those odds, okay? And ideologies, whether it be religion or Marxism or Scientology or anything like that, they always assume their dogmas to be true, right? You're never allowed to challenge the dogmas of any of these group belief systems. And then what they often do, because things don't fit their religious system, they twist or cherry pick their facts or ignore anything that would likely falsify their ideas. That's how they escape the testability idea that science must face. Okay, so it's important. Scientists must reject ideas that don't pan out, no matter how appealing they are, right? If you don't reject ideas when they turn out to be wrong, you're not doing science anymore, okay? And the famous physicist, Nobel Prize physicist from Caltech, Richard Feynman, famously said, it doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiments, it's wrong, right? And then we already said in the beginning, but let's remind ourselves one more time, peer review is what distinguishes science especially. It weeds out all the bad science as best we can. And if it doesn't do so in the review cycle where the paper is first published, any idea that's controversial enough after it's published and been reviewed by a handful of people will often be reviewed by multiple labs as soon as it's published, and which means a lot of ideas that were hot when they first were published tend to be shot to pieces in a year or two after they're published. So I often wait for 4 or 5 years before I take anything I read in the science media too seriously, because a lot of stuff in the science media is not tested yet, and it's bullshit. It turns out to be wrong a couple of years down the road, but science media never tells you that. They don't report an idea was shot down, because that's not sexy like reporting the idea in the first place. And as I said, when you do peer review, you get your worst enemy anonymously allowed to review your work, okay? Our experts are very harsh on any idea they don't think pans out. And so only the best ideas that are undeniable get published. And then I said, even if they're published, sometimes they may be done later when many more people replicate the experiment, okay? So again, because you like your own ideas, it's hard for you to see that, but the scientific community puts it out there for a lot of other qualified people to check your ideas before they publish it. And again, from Feynman, the first principle is you must not fool yourself. And you're the easiest person to fool, right? You really can't be fair about your own ideas because they're part of you and you're very fond of them. It's others who don't have that personal attachment to them that are the best judges of whether you're right or wrong. All right, so again, science versus pseudoscience, you follow the evidence wherever it leads. Whereas a religion or Marxism or any other belief system starts with the conclusion, starts with what's given and works backward to confirm what tells them what they want to hear. Science embraces criticism. Religious systems and pseudoscience are hostile criticism. Science uses precise terminology with clear definitions. Pseudoscience uses all these jargons that make it impossible to tell what they really mean. Science claims are usually conservative and very tentative, where religions and pseudoscience will say very grandiose claims that go beyond any evidence that you can evaluate. Science tries to properly consider all the evidence and arguments, whereas these religious and pseudoscientific systems will pick only the evidence that fits them or relies on individual testimonials, but not actually does any real science, okay? And the science has to be rigorous and repeatable, whereas you often find these crank pseudosciences, they'll do something with one observation only and never repeat it. Science is trying to always engage with the peers community and be an open society, whereas, of course, the people who crank out pseudoscience are often lone mavericks who think they're the smartest person that ever lived. Science tries to follow a careful, valid logic. If you evaluate these pseudosciences, they're often inconsistent and invalid. And science is always changing with new evidence, right? It's never final. And of course, new evidence, as this very graphically says, is something pseudoscientists don't like. Or this little graphic here says it very nicely, science, if you don't make mistakes, you're doing it wrong. If you don't correct those mistakes, you're doing it really wrong. If you can't accept your mistaking, you're not doing it at all. I mean, that says it in a nutshell. All right, let me break now here because we've got quite a long video here. So let me close this window and go back to our screen. And before I end the recording here, let me just point out I'm wearing my shirt for this lecture. I would wear this if I gave you the lecture in person in class. On the front, of course, it has my Skeptic Society logo. But on the back, you can see it here. I can't even see whether I'm in frame. It says Science Rules. I like to wear this here in lots of places, actually. All right, so let's break that part one of our second set of lectures, and I will resume with part two shortly.